Hello everyone, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In this video related to current electricity, we'll introduce the concept of electric current, current density, Ohm's law, we'll introduce resistance, conductance, resistivity, conductivity, we'll derive the color code for measurement of resistance of resistors. We'll study the behavior of conductor in presence and absence of potential difference. We'll introduce the concept of drift velocity, its relationship with the current. We'll study microscopic form of the Ohm's law. We'll study mobility. We'll try to understand what are the limitations of the Ohm's law, and we will try to study what are the problems related with variation of resistance. So we start with electric current. Electric current, how do we define it? The rate of flow of charge through a given cross section of a conductor is called electric current. If delta Q charge flows through a conductor of a given cross section in the time delta T, then average value of current can be calculated, and average value of current is given by delta Q by delta T. Instantaneous current I would be given by limit delta T tending to 0 delta Q by delta T, which can be written as dQ by dt. We like to understand some important properties related to electric current. The SI unit of current is ampere, while the CGS unit is biot. So we have two units of current in SI system, it's ampere, and in the CGS system it's biot. 1 ampere is 1 coulomb per second. I is equal to Q upon T, and charge can be written as an integral multiple of basic unit of charge, Ne upon T. 1 ampere is 1 coulomb per second, and 1 ampere in terms of the number of electrons, it is 6.25 into 10 raised to power 18 electrons flowing per second. The conventional current usually that we mark in the electrical circuits is due to the flow of positive charge and has a direction from positive of the battery to negative of the battery. The conduction current, which is due to motion of electrons, flows opposite to the direction of conventional current. So here we have a conductor connected to an external battery. The direction of the conventional current is in the direction of the electric field, and it is from positive of the battery to negative of the battery. While the conduction current, which is due to motion of electrons, the electrons always flow from a point of lower potential to the point of higher potential, and that is why the direction of conduction current has to be opposite to the direction of conventional current. The current in different type of materials is due to different type of charge carriers. Like in conductors, the current is due to free electrons. So free electrons constitute the current in case of conductors. In electrolytes, the current is due to motion of positive and negatively charged ions. In semiconductors, the current is due to electrons and positively charged holes. So different type of materials, the different types of charge carriers constitute the current. Current is basically a scalar. We can make current a vector when we describe current in terms of current density. The current flowing per unit area of cross section held normal to the direction of flow of current is called current density. Remember, current density is a vector whose direction is along the direction of electric field. Current density, defined as current per unit area of cross section, will represent current density by J, which will be equal to I upon A. And remember, the direction of J vector is along E vector or along the direction of conventional current. What can be the unit of current density? It is ampere per meter square. And how do we write the dimensions? m0 L power minus 2 T power 0 ampere power 1. Now we have put up a note here which says when a current flows through a conductor, no accumulation of charge takes place inside the conductor, because the total charge entering a conductor is equal to the total charge leaving the conductor. It is in accordance with law of conservation of charge. In a conductor system of variable cross section, the current remains unchanged but the current density is different. So if I have this shape of a conductor, then area of cross section in the two parts is different. So I define current density J1, and J1 would be equal to I1 upon A1. Similarly, the current density at the exit point J2 would be equal to I2 upon A2. J1 upon J2 would be equal to A2 upon A1. Remember here, I1 is equal to I2, so the ratio cancels and we have J1 upon J2 as the ratio A2 upon A1. Since the area 2 is smaller, so the ratio is less than 1. So current density J1 is less than J2. Now we come to a very important law called the Ohm's Law. Ohm's Law, how do we define it? If the physical conditions like temperature, pressure, dimensions of the conductor and nature of material of a conductor are kept unchanged, then the strength of the current flowing through the conductor is directly proportional to the potential difference applied across its ends. So V proportional to I. To remove the proportionality sign, we make use of a constant, and that constant is R. So we write it as V is equal to Ri. R is the constant of proportionality whose value depends upon size, nature of the material and temperature of the conductor. This constant is called resistance of conductor. Resistance is the property of a conductor to resist the flow of charge through it. So every conductor resists the flow of charge through it, and that is measured with the help of resistance. How do we represent resistance? The resistance is represented like this. Suppose I is the current flowing through it on the application of a potential difference V. Then I can always plot a graph between them, V and I. So we have two graphs here. One is between V and I, another is between I and V. The IV graph is a straight line passing through the origin O, figure B. Here V is equal to R times I, so R would be equal to V upon I, so 1 upon I upon V, that is 1 upon the slope of VI IV graph. So this is from the figure B I am calculating. Now the reciprocal of the slope of IV graph represents the resistance, figure B. The resistance of a conductor depends on size of the conductor, nature of the material and temperature of the conductor. So what does resistance depend upon? It depends upon three parameters: shape and size of the conductor, nature of the material through which it is made, and the temperature of conductor. The resistance of a conductor is defined as the ratio of potential difference across its ends to the strength of current flowing through it. That is why R was written as V upon I. The SI unit of resistance is ohm. 1 ohm is equal to 1 volt upon 1 ampere. So 1 ohm is defined as 1 volt per ampere. And what are the dimensions of the resistance? M1 L2 T power minus 3 ampere power minus 2. The resistance of a conductor is said to be 1 ohm if a potential difference of 1 volt sends a current of 1 ampere through it. So this gives me definition of 1 ohm. So how do we define? We say resistance of a conductor is said to be 1 ohm if a potential difference of 1 volt sends a current of 1 ampere through it. Now we introduce another quantity called the reciprocal of resistance, that is conductance. Resistance means the obstruction to the flow of charge, and conductance means the ease with which the charge flow through the conductor. The reciprocal of resistance is called conductance. The conductance G is equal to 1 upon R, can be defined as the ratio I upon V, and the unit of conductance is ohm inverse, and it is called as either mho or Siemens. 1 ohm inverse would be equal to 1 ampere per volt. Then we come across another quantity called resistivity. The resistance of a conductor increases due to increase in length because now electrons have to travel a longer distance. So we write R proportional to L. The resistance of a conductor increases due to decrease in cross-sectional area because electrons find it difficult to pass through a smaller cross-sectional area. So we write R inversely proportional to A. Combining both, what do we find? We find R can be written as proportional to L upon A, and to remove the proportionality sign we use a constant rho L upon A. So what is rho? Rho is called resistivity or specific resistance of a material of conductor. What does resistivity depend upon? Resistivity depends on nature of material of a conductor. If we choose L is equal to 1 meter, A is equal to 1 meter square, then rho would be equal to R. So what is resistivity? Resistivity of a material is numerically equal to the resistance offered by a unit cube of that material when current flows perpendicular to the opposite faces of a cube. Right? When unit current flows perpendicular to the opposite faces of cube. Now, how do we define the unit of resistivity? In SI system, the rho is measured in terms of ohm meter. The reciprocal of resistivity, and we call it as conductivity. Like we had reciprocal of resistance, similarly we have reciprocal of resistivity. The reciprocal of resistivity is called conductivity of material. So conductivity represented by sigma, it is reciprocal of resistivity, can be written as L upon Ra. And what is the unit of conductivity? Ohm inverse meter inverse. Now resistors, these are the devices which are used to introduce the resistance in all electrical circuits. Any object of a conducting material having a resistance of desired value is called a resistor. You can have a 1 ohm resistor, 2 ohm resistor, 100 ohm resistor, 500 ohm resistor, mega ohm resistor, everything possible. So carbon resistors are made by molding carbon with a suitable binding agent into a cylinder. Wire leads are attached to the cylinder and the entire resistor is encased in a ceramic or a plastic jacket. Now, how do we measure the resistance of a resistor with the help of color code? So, to indicate the resistance value, its percentage reliability, a color code is used. The resistor has a set of colored concentric rings A, B, C and D on it. Like here, we have the 4 rings A, B, C and D. The first ring would denote the first digit of the measurement, second ring would denote the second digit, the third color of the third ring would provide the multiplier, that is what is the power of 10 with which the 2 digits already found out are supposed to be multiplied. And what does the fourth ring tell us? It tells about the tolerance, uncertainty. So here, what do we find here? A denotes first digit or the first significant figure. B denotes the second digit or the second significant figure. C denotes the number of zeros or the power of 10 by which first 2 significant figures are to be multiplied. D denotes the tolerance limits, that is the error in the value of resistance. Now we have a table here just showing the different values of the color. So we begin from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. And the colors are black, brown, red, orange, yellow, green, blue, violet, grey and white. How do we remember them? B.B. Roy of Great Britain had a very good wife. So if I have a ring of black color, the digit is supposed to be 0. If I have a ring of red color, the digit to be utilized is 2. Now gold, the fourth ring, that is the tolerance ring. If it is made up of gold, it represents plus minus 5% as the tolerance. Silver ring, plus minus 10%. No color, that means the tolerance ring is not present. It represents plus minus 20%. Now just we'll try to use this and find out how do we calculate the value of resistance. For that we have example 1. A voltage of 30 volt is applied across a color coded carbon resistor with first, second and the third rings of blue, black and yellow colors. What is the current flowing through the resistor? The first significant figure we have is blue. It represents digit 6. Second significant figure is black. The digit is to be 0. And the third is yellow, and it tells me number of zeros to be attached to the first two significant figure. So blue is 6, black is 0 and yellow is 4. So the resistance is first digit, second digit and the multiplier, that is 60 into 10 raised to the power 4 ohm. And how much potential difference was applied? It says 30 volt. So one can calculate the current flowing through the resistor by the Ohm's law. I must be equal to V upon R, and it would be 0.5 into 10 raised to the power minus 4 ampere. So the color code helps in determination of the values of the resistance. Another example, just to make us understand the concept of measurement of resistance with the help of the color codes. If the ring A is yellow, B is red and C is orange and D is silver, find the value of resistance. Yellow is 4, red is 2, orange is 3 and silver gives me plus minus 10%. So resistance is 4, 2 and the multiplier is 10 raised to the power 3 plus minus 10%. So it gives me 42,000 plus minus 4200 ohm. So what is the maximum value of resistance? 42,000 plus 4200, and the minimum value 4200 minus 4200. That is, the range of the resistance varies from 46,200 ohm to 37,800 ohm. It tells me the range of the resistance. Now let us come to what are the different types of currents that we know. We understand there are two types of current. One is called the direct current and the other is called the alternating current. Now the current whose magnitude and direction does not change with respect to time is called direct current. Here we are plotting the direct current with respect to time, and see the magnitude and the direction of the current does not change with respect to time here. When I say alternating current, then the alternating current, how do we define? The current whose magnitude continuously changes with the time and whose direction is periodically reversed is called the alternating current. From here by the graph, we are plotting IAC with respect to time. So initially in the first half cycle, the magnitude of the current increases, and in this periodically reverses its direction. After every time interval t by 2, the direction is reversed from positive to negative. So AC has alternative positive and negative halves. The amplitude of AC is a constant. Amplitude means this maximum value, and this remains constant. The magnitude of AC continuously changes with time. See, the magnitude of AC is continuously changing with respect to time. In AC, the direction is periodically reversed. Now what is the frequency of AC? 50 Hertz in India. That is, the domestic AC that we obtain at home is coming at 50 Hertz, while in USA the AC is supplied at 60 Hertz. So dear students, I hope you are enjoying our videos. If you are enjoying our videos and understanding physics, then please subscribe the channel, like the videos and comment to appreciate or ask a question. Now we would like to understand the behavior of a conductor in absence and in presence of potential difference. How does the current travel? How do the charges move inside the conductor? Why there is no current in absence of potential difference? We need answer to such questions. Now it says, when no potential difference is applied to a conductor, then the free electrons move randomly inside the conductor. Their motion is like the motion of gas molecules and is called random thermal motion. The electrons gain energy by virtue of temperature of the surrounding. The speed gained by the electron due to temperature is then called as thermal speed. According to the kinetic theory of gases, kinetic energy half mv square is equal to 3 by 2 kT. So what does Vt represent? The thermal speed, that is the speed acquired by the electrons by virtue of temperature. K is called the Boltzmann constant, has the value 1.38 into 10 raised to the power minus 23 joule per Kelvin. M is the mass of the electron and T is the absolute temperature. So the thermal speed Vt would be given by under root 3 kT upon m. At the room temperature, normally the 27 degrees centigrade, which can be put as 300 Kelvin. Let us calculate what is the value of thermal speed. Substitute the value of K, 1.38 into 10 raised to the power minus 23, absolute temperature 300 Kelvin, and mass of the electron 9.1 into 10 raised to the power minus 31 kilogram. Just solving, we get approximately 10 raised to the power 5 meter per second. A very high value of thermal speed. In absence of potential difference due to random motion, the average displacement and therefore the average velocity of the electron is 0. In this condition, no flow of current takes place. Since the average displacement comes out to be 0, average current comes out to be 0, so one can say no flow of current takes place. Now we would like to study behavior of a conductor in the presence of potential difference. Now let us apply the potential difference. So on applying a potential difference V across the ends of a conductor of length L, an electric field is established inside the conductor. Remember, this electric field is established instantaneously because fields, they travel with a speed equal to the speed of light. This field will exert a force on free electrons, causing their acceleration opposite to the direction of electric field. So what does the electric field do? It exerts a force on the free electrons, causing their acceleration. The velocity does not increase continuously because the electrons continuously collide with the ions and then transfer their kinetic energy to them. So we have already studied in collisions in class 11th, which says when a lighter particle collides with the heavier particle at rest, then the lighter particle transfers its entire kinetic energy to the heavier particle and comes to rest. Due to this, electrons now move with a small drift velocity in the direction opposite to the electric field. What is drift velocity? The average velocity acquired by the electrons in presence of external field is called drift velocity. The drift speed constitutes current in a conductor. So this drift speed is responsible for generating current in a conductor. The drift speed is very small as compared to the thermal speed. Thermal speed, it ranges from 10 raised to the power 5 meter per second to 10 raised to the power 6 meter per second. While the drift speed, it ranges from 10 raised to the power minus 4 meter per second. That is minus 3 to minus 6 meter per second. Now let us calculate a relation for drift velocity. When a potential difference V is applied across a conductor of length L, then electric field established inside the conductor E is equal to V upon L. What is the force on the free electron due to this electric field? Force would be equal to Q times E, and in case of electron, the charge is minus E. The negative sign shows that direction of the force is opposite to the direction of electric field. From the second law of motion, force must be equal to mass times acceleration. Now, from equation 1 and 2, since the LHS are equal, the RHS are supposed to be equal. So we get m times a must be equal to E times c, or the acceleration is equal to minus E upon m, which shows the direction of acceleration is opposite to the direction of electric field. Now what would be the velocity that would be acquired by the electron? We can calculate it with the relation V is equal to U plus AT. So here The velocity acquired is the drift velocity. So we write Vd, initial speed is u, a, and tau is the relaxation time. And what is relaxation time? The time between two successive collisions during which the acceleration of electron takes place. Initial speed 0, acceleration here, so Vd would be equal to minus e tau upon m. The negative sign shows that the direction of the drift velocity is opposite to the direction of electric field. So Vd is equal to e tau e upon m. And remember, E can be written as V by L. So what are the factors upon which the drift velocity depends upon? Let us see. The drift speed depends upon potential difference, length of the conductor, electric field, temperature of the conductor through relaxation time. The drift speed is independent of radius of conductor and the area of cross section. So it is independent, it does not depend upon radius, and neither does it depend upon area of cross section. Let us now find out what is the relation between current and drift velocity. So here in the figure you are able to see we have a conductor here, we have applied a potential difference V across its ends. This would be the point of higher potential and this would be the point of lower potential. The length of the conductor is L, the electric field established inside the conductor is E, and I is the current made to flow. So we have a conductor here of length L, cross-sectional area A, with N as the number density of free electrons. That is number of electrons per unit volume in this material of conductor. When a potential difference V is applied across the ends of a conductor, the electric field causes the electrons to drift from a point of lower potential to the point of higher potential. Here A is the area of cross section, Vd is the drift speed of the electron, E is the charge on the electron, N is the number density of free electron. So how do we calculate number of free electrons in length L of the conductor? So it must be number density into volume of conductor. So N is the number density and A times L would represent the volume of conductor material. The total charge carried by these electrons delta Q would be equal to NaL, the number of electrons, and each electron carries a charge E. Now what would be the time taken by these electrons to drift across the length of the conductor from point P to Q? It must be delta T must be equal to length upon velocity, or the length of the conductor is Vd times delta T. Now what is the current through the conductor? It must be delta Q upon delta T. So delta Q is NaLe. And what is delta T? L upon Vd. L cancels out. So I have obtained the equation of current as I is equal to NeAVd. Ne is nothing but carrier charge density. This equation 1 is the microscopic equation for current. It answers the question, what does the current flowing through a conductor depends upon? And it says it depends upon the nature of the material of the conductor through N. Also it depends upon area of cross section and the drift speed Vd. So whatever are the factors that are affecting drift speed, the same factors would also be affecting the current. Now I like to calculate Ohm's law in terms of J and E, which is normally called as the microscopic form of the Ohm's law. J is the current density and E is the electric field. We consider a conductor of length L, cross-sectional area A. Whenever a potential difference V is applied, then a current I flows through it. The current through the conductor is given by the equation NeAVd and the drift speed given by E tau E upon m. The current density, the ratio of current and the area of cross section, is NeVd from equation number 1. Using 1 and 2, what do we find? J would be equal to N times E and Vd is E tau upon m. So it gives me Ne square tau m, and here is the electric field. So J would be, I can write these quantities in the bracket as Ne square tau upon m into E, or J would be equal to sigma times E, or 1 upon the resistivity times E. E is equal to rho J. So we have the equation either J is equal to sigma times E or E is equal to rho times J. where sigma, which is Ne squared tau upon m, is called the conductivity of material of the conductor. And remember, the reciprocal of conductivity was called as resistivity. So resistivity is m upon Ne squared tau. Equation J is equal to sigma E and E is equal to rho J. They represent the microscopic form of Ohm's law. Some important aspect put in the footnote here. If I current flows on the application of potential difference V, then from the Ohm's law I would be equal to V upon R. The current density J is I upon A. If E is the electric field set up in the conductor, then E was equal to V upon R. So J times A is equal to I, that is EL upon R, or J would be equal to L upon RA into E, and that is nothing but resistivity. So this is another way of determining this relationship. Either J would be equal to sigma times E or J would be equal to E upon rho. These are called the microscopic form of Ohm's law. Remember, J and E are in the same direction. Now, certain important points for us. Conductivity depends on nature of the material through N, number density, free electrons, sigma is directly proportional to N. Conductivity also depends upon temperature of a conductor through relaxation time. So sigma is directly proportional to tau, directly proportional to 1 upon T. So increase the temperature, decrease the conductivity, because by the increase of temperature the random motion increases and therefore conductivity decreases. Conductivity is independent of the dimensions of the conductor, that is length, radius and area of cross section. We have questions many times, if the length of the conductor is doubled, then what happens to conductivity? It would remain unchanged. If the radius of the conductor is doubled, then what happens? No change in conductivity will take place. The unit of conductivity is ohm inverse meter inverse, also called as mho per meter, and the dimensions of the conductivity m-1 L power minus 3 ampere power 2 T power 3. Now resistivity is reciprocal of conductivity, so all dependence, unit and dimensions change accordingly. So we have an example here just to understand. Calculate the conductance and conductivity of a wire of resistance 0.01 ohm whose area of cross section is 10 raised to power minus 4 meter square and the length is 0.1 meter. So the three given quantities written here. Conductance is equal to reciprocal of resistance, and that is 1 upon 0.01, that is 100 ohm inverse. Conductivity is reciprocal of resistivity, that is L upon RA. Length is 0.1, resistance is 0.01 and the area is 10 raised to power minus 4. So solving these we get 10 raised to power 5 ohm inverse meter inverse. Find the resistivity of a conductor in which the current density of 2.5 ampere per meter square is found to exist when an electric field of 15 volt per meter is applied on it. So here J is given, E is given. Using the microscopic form of the Ohm's law, E is equal to rho J. So resistivity rho is equal to E upon J. So that is 15 volt per meter divided by 2.5 ampere per meter square, and that is 6 ohm meter. Another quantity that we come across is called as mobility. How do we define mobility? So mobility is defined as the magnitude of drift velocity acquired per unit electric field. Magnitude of drift velocity acquired per unit electric field, it's a positive quantity. So drift velocity upon electric field, so mu would be equal to Vd upon E. The drift velocity Vd is here, that is E tau E upon m. So Vd upon E is called the mobility. It is E tau upon m, and E tau upon m from the equation of conductivity is sigma upon Ne. So we can write the equation of mobility as E tau upon m or sigma upon Ne. So how do I write conductivity? Sigma is equal to Ne mu. For a conductor, sigma would be equal to Ne, that is number density of free electrons. E is the charge and it is mobility of electron. For a semiconductor, there are two types of charge carriers. So sigma would be equal to Ne into E, mu E, contribution from electron motion and contribution from the hole motion. Ne and H, number density of electrons and holes respectively. Mu and mu H, electron mobility and hole mobility. What is the unit? Meter square upon volt second, and the dimensions are m-1 t square a power 1. Now, there are certain limitations of Ohm's law. The materials for which the VI graph between potential difference and the current is a straight line passing through the origin. A straight line passing through the origin are called as ohmic materials. These materials obey Ohm's law. The slope of the curve tangent theta is dy by dx, di upon dv, that is 1 upon resistance. So resistance is nothing but reciprocal of slope of the VI graph. So we write here resistance as 1 upon the slope of VI graph. There are certain materials where proportionality of V and I does not hold. What are the different types of deviations that we can see? I ceases to be proportional to V, like it just bends here, figure 1. So we do not have a straight line passing through the origin. Such a device is called as non-ohmic. The relation of V and I depends on sign of V. If I is the current for a certain V, then reversing the direction of V, keeping magnitude fixed, does not produce same magnitude of current in the opposite direction, figure 2. If I apply a positive potential, you see the current increasing non-linearly. But if I reverse V, then the nature of the curve changes. This is nothing but the VI characteristic for a diode, which we are going to study in the last chapter, semiconductors. VI curve for gallium arsenide. Just see, it has different regions. It has a non-linear region here. It has negative resistance region here. Initially it's more like a linear curve, then it is having non-linearity and the slope then starts decreasing. So we have a different type of VI curve for gallium arsenide. The relation for V and I is not unique. There is more than one value of V for the same current I. Example, gallium arsenide. The relation for VA and I is not unique. There is more than one value of I for the same voltage V. Just imagine, if the voltage remains the same, then I have this value of current, this value of current and this value of current. Such a graph is for a transistor. So we have a diode, a nonlinear device. We have a transistor, a nonlinear device. We have gallium arsenide, a material that would be used for making semiconductor devices. Now the question is, how does resistance change? How do we have an idea about what type of relations to be utilized when problems involve change in length, change in area of cross section and so on? So I have divided the problems in 3 categories. Category 1. See, resistance R is equal to rho L upon A. Rho is m upon Ne square tau. So R can be written as m upon Ne square tau. It depends upon length, area of cross section. It depends upon N and it also depends upon temperature. So resistance is directly proportional to length if rho A are constant. It is inversely proportional to area of cross section if rho and L are constant, both of them coming from this equation. R is inversely proportional to the number density if tau A L are constant and only depends on nature of material. R would be inversely proportional to the relaxation time or directly proportional to the absolute temperature if area, length, N are constant. So R would depend upon temperature through relaxation time. These relaxation or these equations are only valid when one quantity changes at a time. Like I have a roll of wire. Once I compare, I cut a wire of length 1 meter and then I cut a wire of length 2 meter. The resistances would be in the ratio 2:1, because in this duration neither temperature is changing, nor the nature of material is changing, nor the area of cross section is changing. It is only the length that is changing. So these equations to be taken into account when one variable changes with respect to time. Let us see the second category of the problem. There are certain problems in which mass of the material, volume of the material remains unchanged. These involve with words like stretching. The wire is stretched to double its length. The wire is melted and it's converted to a wire of double the area of cross section. The wire is recasted into another wire of double the length. If such words exist, then we need to manipulate and obtain the different types of answers that have been expected of us in the problems. The resistance of the wire R is equal to rho L upon A. I can multiply by length and divide by length, makes no change, can be written as rho L square upon V. Rho is constant and volume is constant, so R is proportional to square of the length. Used in the problems where length is stretched 2 times, 3 times or n times. If it is n times, then the resistance becomes n square times. Now, initially we multiplied by length, now multiplied by area of cross section. So length into area, volume upon A square. So R is inversely proportional to A square. This would be utilized where the wire is stretched to reduce the area to half or 1/3 of its initial value. If it is reduced to half, then the new resistance would be 4 times. Now, in the same relation, area can be written as pi r square. So the relation becomes rho v upon pi square r power 4. R is called the radius of the wire. This relation to be utilized where wire is stretched to reduce the radius to half, 1/3 or any other value. So every time what we observe is we convert our equation to a single variable equation to handle the questions. Now let us come to the category 3 of the problems. Problems involving percentage change in resistance due to percentage change in length, area or radius. Like question says, the length increases by 1%. What is the percentage change in resistance? So for such questions, we require some different way of working. Again, I have R is equal to rho L square upon V. I can take log of both the sides. So log R would be equal to log rho plus 2 log L minus log V. Rho and V are constant. So when we differentiate, the differentiation would be 0. So dr upon R would be equal to 2 dl upon L. So we get a relation dr upon R, that is change in resistance upon original resistance. If multiplied by 100, it gives me percentage change in resistance. And on the right hand side, it is 2 dl upon L. Suppose the length increases by 1%, then the resistance increases by 2%. We can have a direct answer from here. Remember, all increases are taken positive and all decreases would be taken negative. There are certain problems involving percentage change in area. So we have here rho v upon a square. Take log of both the sides. So log rho plus log v minus 2 log d a. Then on differentiation we get dr upon r would be minus 2 dA upon a. Like if area increases by 1%, then the resistance decreases by 2%. Remember, the negative sign shows a decrease and a positive sign shows an increase. For problems involving percentage change in radius, so r would be equal to rho v upon a square could be written as pi square r power 4. Just take log of both the sides, differentiate, and we have dr upon r would be minus 4 dr upon r. This is called percentage change in resistance. This is percentage change in radius. Now keep a precaution here. And what's the precaution? Use these percentage change relations in equation number 1, 2 and 3 when the changes are less than or equal to 5%. Very important thing. We must know where to use a given type of relations. Now let us pick up an example how to apply these. The length of a wire increases by 1%. Find the percentage change in resistance. So dl by L 1%. So for length change, dr by r was equal to 2 dl by L. So dr by r would be equal to 2%. If the length increases by 1%, then the resistance increases by 2%. It reduces the length of calculation for us. The area of a conductor increases by 2%, then the percentage change in resistance. So dr by r is minus 2 dA by A. So it is minus 2 into 2, minus 4%. That is, I can say, if the area increases by 2%, then the resistance decreases by 4%. We have another example here. The radius of a conductor is increased by 1%. Then find the percentage change in resistance. So for change of radius, we have minus 4 dr by r. So here, if the radius increases by 1%, then the resistance decreases by 4%. See the simplicity of solutions. Another example here, the area of cross section of a wire decreases by 10%. Find the new resistance and percentage change in resistance. See, the area is decreasing by 10%. So I cannot use the approximate relations that we have derived. We now want to make a perfect full calculation to obtain the answer. Let us check. R was equal to rho V upon A square. A is the initial area and let the A dash be the final area of cross section. What would be the value of A dash? It is A minus 10%, that is 9A by 10. So the new resistance R dash would be equal to rho V upon A dash ka square, that is rho V upon A square 100 by 81. That is, the final resistance and the initial resistance are just related like this. How do I calculate percentage change of resistance? Percentage change means final resistance minus initial resistance upon R into 100. So 100 by 81 R minus R upon R. So this gives me 19 by 81 into 100, and that solution gives me 23.46%. Had we calculated by the approximate relation, the answer would have been 20%. So see, a large deviation in the answer might have taken place, and that is why we have put a limiting condition that use the percentage change relations only when the percentage change is less than equal to 5%. So dear students, I hope this video would be very useful for you. You are requested to subscribe the channel and press the bell icon button to obtain the notifications of new videos in time. See you in the next video. Thank you.